Okay, so let's hope that on a late Friday afternoon, after doing 3 classes and maybe a couple thousand calculations today, then I still have a little something left in the tank without making a lot of careless errors. I should have already had a marker with me before I started this. I guess I got one in the pocket. So I had a request to do some limits. And, in math, you can come at problems a lot of different directions. Maybe there's more here with a calculator, sure, symbolically, numerically, graphically, geometrically. And we'll come at these limits a couple of different directions too. So we've been working with this particular calculation quite a bit in class, and I thought we'd maybe look at it a little bit from a graphical standpoint as to what's going on. We talked about numerically infinity. We've been using the number 100, which isn't all that big, but it's usually big enough to get a feel for these calculations right off the get-go. So if we put 100 in here, then these terms do come into play a little bit, but not a lot, especially if you put 1,000 or 10,000 or 100,000. So we talked about when the powers are the same, it's the ratio of the coefficients, but I thought I'd look at it from a little bit of a graphical standpoint. So just a couple of words on limits to begin with, exposing you to them now because your next level of study is based on limits. So I think you should have a little feel about the conversation before you get there. So limits are, I like to think of them as trajectories in a table. You know, when we do y equals x squared, we got, -3, 9, -2, 4. We create tables. And so as we approach different x values, we're really looking at what's going on the y side of the table. Can I make a statement about, geez, I think we're headed towards this number, or I think we're headed towards this pattern. That's what really limits are. Well, limits are numbers. Patterns can be, slant asymptotes and quadratic asymptotes, things like that. But let's take this from a graphical standpoint, this problem here. So x squared, let's just elongate it a little bit, is this distance from the x. So that's an x value, and I squared it, so I get that y value. If I have one above it that's twice the size, then I get that y value, which means that this is twice that. Okay, if I go and 2x squared, I want to get a couple of these in here before I graph. So there's one y value for x squared. This is x squared. 2x squared will be above it, twice as high each time. So I think I've got a little bit of the trajectory here. So that y value, this y value should be twice that one for that x. And that's a ratio of change that's not going to stop. It's going to continue to infinity. So if I divide numerator by denominator, I'm actually getting that ratio of 2. And this actually shows up in L'Hopital's, when you study L'Hopital's, a rule called L'Hopital helps you find some information next year. To actually understand it conceptually as x goes to infinity, you actually have to have a little of that picture in your head. Okay, but I'm not talking about that now. But this concept of seeing the relationship of one graph to another is something you want to develop. It helps your mathematical thought process. Okay, so hopefully you memorize the rule, and so that if all of a sudden I said, okay, this is now 12 and that's 7. Okay, as I go to infinity, what does it go to? Well, it goes to 12 sevenths. Why? Because when I put a billion in here and I square it, what have I given you? 9 zeros with a billion? So it's 18 zeros. Whereas this one has 9. Well, this thing then is 1,000,000 times bigger than that. All right, so these things drop out of the picture. They drop out. And also if you did 12x squared over 7x squared, if you realize that, then that divides out of the problem too, as you put numbers in. Okay, so hopefully you've got a feel for that. Let me get this out of the way so we're not looking at it anymore. Now, what happens if the denominator is bigger than the numerator? So from a standpoint of a graphing standpoint, that's going up very quickly eventually. This continues to go in that direction. Well, if I pick this x value here, then I have that height for my numerator. I'll write that as a numerator. So that's my amount numerically as represented by that altitude. I don't even think I can reach high enough. That's going, yeah, I mean, that's way up there, right? Even from a small picture like this. So the question is, how many times will the denominator altitude, which I can't even draw far enough, how many times will that altitude fit into this? I hope you say it won't. It doesn't. Okay, from a numerical standpoint, we have, again, when we go to really big numbers, if you're a billionaire, you really don't care if you give the cabbie a $6 tip. It's nothing off your back, right? Hope you do give a little more than that, by the way. If you're a billionaire, it'd be nice. All right, so that doesn't matter. That doesn't matter. Not when we're going to infinity. And honestly, that doesn't matter either. Okay, it's the big players in the numerator and denominator. And from a numerical standpoint, what does this reduce to? From your algebra 1 days, I hope you're saying 5 over 7x. So let's multiply x by 7 by 10. All right, 70. Let's multiply it by 100 because I want to go to infinity. So let's let x equal 100. 100 times 7, 700. 1,000 times 7, 7,000. More zeros, more zeros, more zeros, more zeros. Well, I hope you have a feeling for the size of that fraction. I hope you can say, oh, that's going to 0. So what's the rule? The rule is if the exponent is bigger in the denominator than in the numerator for these rational functions that we're graphing now, you know the end behavior. When I say end behavior, I'm saying big numbers for x. Okay, local behavior is when x is close to 0. And as we move to bigger and bigger numbers, there's a definite tendency here to end up with a smaller number. Okay. All right, so now let's look over here at y equals x minus 3 over 2x plus 4. Can you just answer it based on what we did a minute ago? Well, I hope so. You pause the video, obviously, each time I ask these questions now. Well, they're both the same exponent. So that is a 1 in front of the x. So this is, oh, I didn't even write a limit, sorry. So what is the limit? Hard to answer a question if I don't give you the proper command, right? Math is a language and I didn't use it just then. So 1 over 2. Right, I'm hoping you get the gist of this. What happens if I make this a 4 and this a 5? Well, it's going to 0 because that's bigger than that. So I guess we're doing a little rapid fire 5 here. What happens if that's a 14 over a 5? Well, it's not getting small anymore. It's getting big. All right, that thing's getting so much bigger faster. You know, I got a numerator, I got a denominator. This is getting bigger faster than this. Let's put some numbers in here. 4, boom, 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 3. That goes in a lot of times, right? Because the exponent's bigger. So that's what you'll be studying next year anyways, rates of change. So you want to start thinking about them now. All right, how about this one? Oh, whole different ball game here. So as x goes to 2, well, we know as x goes to 2, well, you can pause the video and think about it, obviously. It's undefined. 2 minus 2 is 0, and you can't divide by 0. And people get stuck on this. But the language is as x goes to 2. It's not what happens at 2. It's all about what happens as it goes to 2. And there's a plus sign here. Well, there's 2 sides to the number 2 on the x-axis. One that's above and one that's below. So we're going to pick numbers like 10 and then go to 9, 8, 7, 6. I did that too quickly to get close to 2. Going to get to 3 and then 2.5 and then 2.1 and then 2.001 and see if there's a trend in the table. All right, so let's actually do that. So I picked some nice even numbers and we're going to go to 2 from, let's do it here. We're done with that problem. So let's go to the number 2 from above, although in a table, I'm going to come in from this direction, right? 10, I'm picking even numbers because I think that it's going to be nice to divide by even numbers. Let's see, I got to start lower for this particular problem. 12, 10, 8, 6, 4, 3, 2.5. I think I'll say 1/2. Mathematicians like fractions. 2 1/4. 2 1/8. Maybe that's enough for us to see. All right, so we put 12 in. 12 minus, that didn't really help me, but 12 minus 2, so 12 tenths. Okay, then I put 10 in. 10 minus 2 is 8, 12 eighths. Not friendly integer numbers yet. I thought I was going to do that. 8 minus 2 is 6. 6 and a 12, 2. Well, 2 is bigger than that, by the way. And that's bigger than that, by the way. So we put a 6 in. 6 minus 2 is 3, goes into 12. 4, we put a 4 in. 6, we put a 3 in. 12, we put a 2.5 in, 2.5. Let's start here with 2.5. 2.5 minus 2 is a half. How many times does a half fit into 12? 24. Now we're going to do 2 1/4, so that's going to become a fourth. How many times does a fourth fit into 12? 48 times. I put an eighth here, 2 1/8, right? 2 1/8 minus 2, hope everybody's with me, gets me an eighth. That goes in 96 times. Any idea where we're headed? Because I could make this 80, 800, right? It's going to get bigger and bigger and bigger. So where's it going? It's going to infinity. Now, from a graphical standpoint, we started graphing these things. Yeah, an asymptote at x equals 2. From our earlier ones, we know that this goes to 0 as an asymptote, right? Because that's x to the 1, this is x to the 0, x to the 0 is 1. So this is bigger than that. Not that you'd ever write x to the 0, but okay, that keeps getting bigger and that's constant. So the bigger this gets, the smaller the fraction gets, right? So it goes to 0. And it's certainly positive, so it looks like that. And we started at 12, and we kept moving closer and closer to 2. And what happened? Our numbers kept getting bigger and bigger, going to infinity. So I hope that's a little practice. All right, so we got 2 more problems to look at. All right, so I just put a little graph up there. All right, so this is a point of discontinuity in what I drew. And 4 gets you 7. So what happens is I go to 4. Well, it doesn't equal 7, but it sure as heck approaches it from both directions. So we say that f of x equals 7. Whereas over here, if I go back to this problem, let's go back to this problem briefly. I'm just putting some thoughts in your head at this point. All right, I'm not going to hold you too accountable for this. Next year you will be, of course. But I'm going to ask it. I want you to learn it. So I don't know, maybe I should withdraw that statement. Maybe I should hold you totally accountable for it. So minus, what's it mean to come in from the other direction? Well, from the other direction means that we're looking at 2 here, which is undefined, still undefined. Let's put it here, right? And we're coming in from below, from the negative side, from this side. Okay, so we're looking at numbers like 0 and 1 and 1 1/2 and 1 1/4 and 1 1/8 and 1 1/16. So what happens when I put those numbers in here? We get a sign change. Can I cut right to the chase? 1 1/16. Okay, so if I do that, I end up with, I meant to say, I butchered this. I apologize. I told you it was late. So 1 1/2, I should have done 3/4. I should have done 7/8. I should have done 15/16. Okay, so now when I do 1 15/16 minus 2, I end up with negative 1/16. So I get a sign change. But 16 times 12, 160, and 32, 192, I think. I think I'm getting minus 192 as an altitude. So this is coming in from this direction. This is going to that direction. But as I come in from the left, I'm going to negative infinity. And I go to the right, positive infinity, which means the answer to this one is negative infinity. That's this pictorial situation there. If I don't put a plus or a minus, then I'm saying, hey, come in from both directions. Well, I'm not going the same place. You know, grandma's going to Montreal, and then she's going to New York at the same time. You know, basically the same time. It's kind of hard to picture where she is. You know, and that's why I had to go get her in Albany. She had a little moment. Too bad. But the opposite of this picture is this picture where, well, hey, we're going to the same destination. Yeah, we're going to Montreal. There it is. So that's why that's that. I'm just trying to put some ideas in your head here, all right, before you really start studying them more carefully. All right, so here's, you know, just like those chess videos. You know, Carlsen's about to make them. Wonderful move. Can you spot it? There's a limit on this side. See if you can spot it. Let's see if you can spot it. And then we'll write the question that would have been asked. And then we'll do it graphically. All right. Oh, I don't have to wait for you. Pause the video. All right. So what's happening here? Well, if you look, these are independent variables. It's like the hand of a clock. Well, we don't use clocks too much anymore. Yeah, we do. It's up there. All right. So we look at the rate of change here. Well, that's 16. That's 8. What's that? That's 4. That's 2. Well, what am I doing to these numbers? Something's being cut in half. Well, immediately I start thinking about that. That's what I start thinking about. Exponential decay. The exponential decay fits that model. And it sure looks like I'm cutting something in half. What am I cutting in half? Well, I started with 39, I think, didn't I? I started with something to the 0. Why did I pick 39? I wrote something there before. Well, I guess I got to write this here. So I started with 39, I cut it in half. So no, that's not the number I started with, no. Oh, I'm sorry, it's Friday, we're heading towards something here, right? So we really have to establish that first. And I hope you did. Hope you can see that a 4th and an 1/8, I'm slowly moving to this number. So what this really was 32 1/2 to the x plus 7. That's what created that table. Okay, guys getting tired here. So what would the question have been? The question would have been the limit as, and I hope that you would have put a 0, 39 here, and I hope this brings back some memories. You went up 16, right? Just to kind of bring you back to speed. That's 8, right? Because I'm going to be testing you on this, and that's y equals 7. Okay, and then that's 4. And, we're headed to 7. So I hope you see it numerically. I hope that means to you a little bit more to you there. So as x goes to infinity of 32 1/2 x plus 7, well, as this number gets bigger and bigger, what happens to 32? Goes to 16, goes to 8, goes to 4, goes to 2. It's disappearing. What isn't disappearing? The value 7. Okay, so limits are trying to get a better feel for calculations. It's going to force you to what's going on here. And the more you go up the ladder in math, the more you got to, what's going on here? Things don't come to you immediately. All right, it's not as easy as 2 plus 2. So you got to give it some thought. So I hope that that honors the request to some degree. And feel free with a month to go in the term to ask me to do rapid fire this or that. It's your education. I'm asking you to learn how to learn. That means you got to be proactive and you got to take steps. We'll see if, people start asking me, hey, can you do this one? Can you do that one? I'm happy to do them. Doesn't take long. Okay, ciao.